Okay, this is the second piece or second notes video on the 11.5 section, and we're just going to deal with one more idea, and I think it's important to treat it as its own topic because I think just is easier to understand sitting by itself. So we've got this is the little screenshot just of the one little piece of the notes that we had talked about doing in a separate video, similar solids. So two solids, and solid is just a three-dimensional shape that have the same type. So they're the same sort of three-dimensional shape. They have equal ratios of corresponding linear measures such as heights or radii, or it's a radius, so multiple radius called radii, are called similar solids. The ratio of the corresponding linear measures is called the scale factor, and if two similar solids have a scale factor of k, then the ratio of their volumes is equal to k cubed. So let's talk about what that means. To be similar means, let's say so just going back in time, to be similar means if we have, let's say a rectangle, and it has a 3 and a 5 for our length and our width, and then we've got a bigger rectangle that is similar to it. For it to be similar, there's a scale factor that gets applied. And let's do a times 4 scale factor. Just it's a good enough number. It's one we can keep in our heads. 3 times 4 is 12. 5 times 4 is 20. So then you blow up each of the sides by that amount. So when you look at the sides, just like if you compare, I'll just get a highlighter here. If you compare this side of 3 to this side of 12, then what you do is say, okay, well, in that scenario, to get from 3 over to 12, what we did was multiply by 4. And that's if you're just talking about a side, so a single side of a shape. And the same would hold true, of course, with the 5 and the 20. If we're talking about the area, and this is an idea we saw when we looked at similarity, but it's a challenging one when you first encounter it. If you think about area, the area of this rectangle is 3 times 5. That's 15. The area of this bigger rectangle is 12 times 20. Well, 12 times 20, that's 240. So 12 times 20 is 240. Notice that is much bigger than a 4 times multiplier. And so we can actually figure out what that multiplier is if you just think about each of the sides is getting hit with a 4-time multiplier, which means the area is side times side. So the area is actually getting hit twice. It's getting hit with 2 times by 4s. One for the length and one for the width. In other words, 4 and 4, well, that's times 16. So when you do an area, you're not just doing a single scale factor multiplication. You're doing both pieces, the length and the width. So that means we're taking 15 times 16. Well, let's go to the calculator and just make sure that gives us our 240. 15 times 16, it better. And there's our 240. So what that's saying is, okay, you got a much bigger jump that's going on when you go from area to area and when you go from side to side. The scale factor, k, that they're talking about is just what happens when you multiply one side, like a 3 to get to the 12, the yellow side. But when we learned about area, the scale factor was 2 of those k's, so 4 and 4. So again, when we talk about sides, we talk about things like inches. When we talk about area, that becomes inches squared. And the idea there being you're hitting 2 different pieces, that's squared. Well, 4 times 4, that's 4 squared, that's 16. Now when we jump to volume, and when we do something with 3 dimensions, now all of a sudden we're not talking inches or inches squared, we're talking inches cubed. So that 4 that with an area situation happened twice, with a side situation happened once, now with a cube, it's going to happen 3 times, and that's where this k cubed is coming from. So in this case, if we had 2 solids where one was 4 times as big as the other, the volume is not going to be 4 times as big, it's not going to be 16 times as big, it's going to be times 4 times 4 times 4. 4 times 4 times 4 is 64. It's going to be 64 times as big. To show what I mean by that, or a for instance, let's think about, let's see, I got enough space here. Let's think about these rectangles. If I have a 3 by 5 like this, well, if I have a 3 by 5 and I were to make a rectangular prism off of that, so let's kind of draw our perspective in here. There's our rectangular prism. And let's say that rectangular prism, let's give it a height of 7. So I'm laying it on its side. Here's our base. That's our area. There's our 15. There's our height of 7. Well, volume of that would be 3 times 5, which is the area of the base, that's our 15, times 7, that's our height. So 15 times 7, well, let's see, 50, I'll just make sure I don't make a computation error as I'm working through this example. That'd be 105. So that means our volume is 105. Well, now let's do our 4 times scale factor. So again, blow up each side by 4. Well, the 3 becomes a 12, the 5 becomes a 20. We saw that. So then all of a sudden this 3 by 5 shaded thing gets a lot bigger, right? So it's here. And it's going to be, what do we say? That'd be 12 and 20. And I'm intentionally making it a little small just because I know I'm going to run out of space trying to draw this. And actually what I can do here, I'll switch colors on it so we can at least see it sticking out. So now this 7 also has to get multiplied by 4. So that's going to become 28. And that thing is huge now. So there is our big prism. Each of the sides got hit by a multiple of 4, but now the volume, when we go get it, 12, 20, and 28. That's a huge number, 12 times 20 times 28. So 12 times 20, again, each unit being hit by 4. So 12, 20, 28, 6,720 is the volume. So that's 6,720. And again, in this case, what I was saying, inches. So that would be inches cubed. And this one would also be inches cubed. So now what we're saying, or what we're after here in this lesson, is not, hey, can you draw these pictures? But it's, can you get from this 105 over to this 6,720 without doing this? Well, you can if you know the scale factor is 4. All that means is I need to take that 105 and multiply it by 4 3 times. 4, 4, and 4. That is 64, and I'll highlight that just so it's clear where I'm getting that. That's this. So look at that highlighter. That's pretty good, actually. So 4 times 4 times 4 is times 64. So what I need to do then is I need to take that 105 and I need to multiply it by 64. And I should get 6720. So let's go over to our calculator. Let's do 105 times 64. Hit enter, and there's our 6720, and we've got our match. And again, the idea here being when you do area, you multiply by 2 scale factors because you're talking about 2 sides, 2 dimensions. You're doing inches squared. When you do volume, now you're multiplying 3 things by 4. You're multiplying the 3, the 5, and the 7. 1, 2, 3. All of them by 4, making all of them bigger, meaning you need to apply the scale factor 3 times. So this little statement of k cubed, what that means is take what the scale factor is and use it 3 times multiplied. A for instance or an example from your textbook on it is right down here. So I cut out an example that we can use, and you don't have a picture of this, so I would ask you just follow along, or if you're so inclined, you can draw a cylinder. And cylinders are actually kind of fun to draw. You just draw a circle, make it a little bit flat. You can notice it's a little bit flatter just to give it some perspective. You drop a line down, you draw a half arc here, and then you do a little dotted line to give it some perspective. So you could certainly draw these 2 cylinders, cylinder A and cylinder B, and they're asking for us to find the volume of cylinder B. And you notice what they did for us was they gave us the radius here, they gave us the radius here. That gets us our scale factor. So we're saying 4 times some number is going to get me 6. Well, this is a pretty easy algebra thing to solve. Divide both sides by 4. And that scale factor, or that sum number, is 1.5. Okay, and that's being applied to the side. Well, now I've got the volume. The volume is 112 pi. So now I'm going to do times 1.5 3 times. So you can either literally write times 1.5 times 1.5 times 1.5, or you can do your 112 pi times 1.5 cubed. And 1.5 cubed is literally 1.5 times 1.5 times 1.5. It's just a slightly more concise mathematical way to write it. So let's do that. Let's find that volume. So 112 pi times 1.5 cubed. And I'll show a couple of different ways to actually write the answer. So let's see, 112 pi times, and then we're going to go 1.5 cubed. Cubed is a tough one. We can literally type it out 3 times, or there's usually a little caret, an up arrow. And that's for any power. You could do squareds that way, but you have a squared key. Most calculators do, but then they don't come with additional keys. So you just do that little up arrow and then 3, and you hit enter, and we're going to get 1187.5, we'll call it. So 1187.5 inches cubed. You'll notice that's a decimal approximate, and they gave the volume as 112 pi. So they gave it as an exact, and I'm going with a decimal approximate, meaning I'm mixing one way of expressing the answer, and they gave us the other way. If you want to leave it in the exact form, you certainly can do that. So let's break it out that way. So let's go 112 pi times 1.5 cubed. What I'm then going to do is I'm just going to think of the pi separately, and I'm going to do 112 times 1.5 cubed, and I'm just going to leave the pi separate. So I just do the numbers times each other. So I can go over to the calculator. We'll do 112 times 1.5, my little up arrow, and cube it. Hit enter, and I've got 378. That is then the volume times pi. So 378 pi inches cubed would be exact. And if you want to check or verify that that's true, we can just do 378 pi in the calculator, and we better get this decimal approximate. So let's do that. We've got a few minutes here. So let's do 378 pi. And when I hit enter, I should see there's that same 1187.5 number that I'm seeing up here that I got before. So they're the same thing. And we talked about that previously in chapter 11, that sometimes you're going to see it written one way, sometimes you're going to see it written the other. If you have the pi in there, great. If you don't, that's fine. It just depends how they ask you the question. But on this one, what they don't want you to do is go and try to figure out what the other dimensions are. You don't need to. Once you've got that multiplier, you just say, okay, to get from one little volume to the big volume, you're going to multiply by it 3 times. And that's the idea of similarity within solid shapes.